Okay, welcome everyone to lecture 13, I believe. Um, so I didn't have time to draft some fancy announcement slides, so I'm just going to do them verbally. So to begin, I thought it would be good to run over the rough calendar for the upcoming weeks. We're rapidly approaching the end of the semester, so it'd be good to sort of get your bearing on what's going on. We are at where are we? We're at this week right here. So today, Tuesday, we have CS4, which is going to be the final CS lectures. As a note on CS4, it's a bit more extensive this time. You do a lot more coding on your own. Hopefully it's more exciting, but also it'd be more challenging. So I would recommend starting early and definitely coming to us if you have any questions. Um, CS4 is due this Sunday, and I believe Aditya is holding office hours from 6 to 7 this Thursday. So
Yeah,
try to take a look before then.
yeah. And I wrote the assignment all by myself, so hopefully I can answer questions on it decently well.
And then Thursday is group meeting as normal. Looking into next week we will not have lecture on Tuesday. We will have a group meeting on Tuesday. And this is to give you a bit more time to prepare for next Thursday and next Tuesday, which are both mock project proposal presentations. So these are trial runs for your actual project proposal presentation. It's a lot of P's, which will be on December 5th. That's a Saturday. Um, so we're going to be releasing more information on the actual presentation and the mock presentation by the end of this week. And so the mock project presentations will bring us right up until Thanksgiving break. And then after we come back from Thanksgiving, we have the final mental health workshop and then a final group meeting before the presentations. As for the remaining assignments, so these two actually are placed incorrectly on the calendar. They should be shifted one cell up. So the project proposal document, which you guys hopefully have started or at least looked at now, it will be due November 21st, so in 11 days. And as I just said, the presentations will be on December 5th. And then one other announcement, some people have been asking about enrollment. So like this semester, we're asking that students enroll in ULAB for 2 units. We'll be keeping this time, so Tuesday, Thursday, 7 to 8 p.m. It might be good to keep that in mind if you're enrolling for classes. And we will be sending out enrollment codes later in January once the semester has started, so you guys don't have to worry about enrolling right now, and you certainly shouldn't worry about using ULAB to satisfy any like phase 1 classes. Okay, so with that, let's begin the final CS lecture.
All right, I'm gonna take over screen sharing then. Okay, so this is gonna run pretty much like the previous CS lectures in the format, in that it's just gonna be me talking over a Jupyter notebook. However, that is not actually the structure of your final CS module. So CS1 through 3, the modules were, you do these checkpoints in a Jupyter notebook, like I've got over here. But this time your assignment is actually going to be writing in Python source files. And so that's like important to step up, and the module explains why that's necessary. But I'll still be lecturing in a Jupyter notebook because, different tools for different purposes. So the purpose here of the next 45 minutes we're going to spend is to get you acquainted with the libraries and best practices for when you're coding out in the real world. You've learned a lot of like basic Python about like, here's how you write a function, here is for loops and string manipulation and all that. And of course that will come up, and that's an essential base of knowledge. But a lot of your work in the day-to-day is going to be through libraries that have a lot more functionality. For example, why we need NumPy. For example, you might have seen like earlier we were defining lists like this. A is 1, 2, 3. And if I ask for A times 2, that doubles it up. But what if I'm actually working with like numerical data and I wanted to say like multiply every element by 2? Okay, before we introduce NumPy or anything, how would we do that? Just as a refresher. I want an expression here that is equal to like 2, 4, 6. Anyone?
You could just index into each element. You could do like a for each in, or yeah,
Okay.
list comprehension. There you go.
Yeah, so that might work some. So yeah, you said list comprehension also. I like that better
Someone in the
because
chat.
then that I can do that just in one line. I can do 2 times x for x in A, and that gets me 2, 4, 6 like I want. But you can imagine that like trying to scale up programming like that gets a little like weird, because what if I'm just trying to like add together lists of numbers, which is a really simple operation. But if you try to do it here, I can do, I mean, it's just more of the same of like, it'll add them as list items. It'll say 1, 2, 2, 3 instead of being like 3, 5 like I'd want. So the immediate workaround for that is the NumPy array. Oh, sorry, I just saw in chat there are a couple of people who are saying the same thing. Yeah, thank you, Vibu and Yongxi, for that. So the need for a NumPy array is I want a list structure that I can do math with, basically. And the initialization of a NumPy array is pretty simple. It's like just about the same as a list. So now instead of just 1, 2, 3, I'll say A is, or let's name it like C, just so this doesn't clash. And p.array 1, 2, oh, sorry, I hit the wrong button there. Okay, 1, 2, 3. And this still works pretty much the same as a list in some regards, meaning I can still index into it. I can ask what's the element at index 2, and that's going to tell me it's 3. But now I've got some nice features. If I try to do multiplication, for example, it'll do 2, 4, 6 automatically, and I can add together 2 arrays like this. And that's actually going to give me 3, 5. Okay, so I took lists and I gave them arithmetic operations. So what, you might be thinking? This will actually come up, like this will turn out to be really useful when you have to do an operation on a lot of things all at once. So one thing that I think it's important for scientists to learn is there are ways in Python to do things in linear time and in constant time. And there is specific meanings to those that are not very important unless you take like CS61B or something advanced like that. But essentially that means there are ways to do certain operations that mean you have to do something once and mean you have to do something in a for loop for every element in the array, which doesn't matter much at our scale. Like our list comprehension up here ran pretty fast because I'm only dealing with 3 elements. But so it's pretty much equivalent to say this and that. But you could imagine if I had a list of 1 million numbers, that might not be quite the same comparison, because essentially when in the list comprehension, what I'm doing is I am doing like for x in a 2 times x, or like y dot append 2 times x, where I'm defining like y as an empty list. I'm not even going to run that. Slow if A has a lot of elements. Plus it just gets to be like kind of a pain. So the 2 advantages of NumPy, I would say, are it saves you the programmer time and it saves your computer time as well, in that a lot of things are going to happen faster. So I've talked a lot about like operations being faster. Let's look at a concrete example of that. Let's say I've got this function that does square plus 5. It takes a number in and it returns its square plus 5. And I actually need to check if this is a valid operation on arrays, or if, yeah, it is, okay. Because there are some things that you can't directly apply to arrays, and there's one more step that you have to do for that. But anyway, if I wanted to do this on, say, a list, I would have to do something very similar to what I did up here. I'd have to say like square plus 5 of a, or that's consistent to use x for a list element. And you get that, and that works fine. But if I've got the numpy array C, I can just do that operation directly. So I'm applying a function onto all of these things at once. And if you look, if you were to open up a, you know what, let's do that. Let's try like a really big input and see if we can notice like a second's delay. I'm not entirely sure it'll work, but let's see. Let's say I've got like list nums is list range int 10 1e6. So that's like the list of all the numbers up to 1 million. And then, oops, I forgot one over here. And the array of numbers that's the equivalent to this is np.arrange, which is just exactly the same thing. It's like a range, but with the numpy array. So a range 0 int 1e6. And you can look at both of them and show, whoops, that's way too many. Oh my God, it actually printed out all of them. Yeah. Oh yeah, NumPy condenses it for you when you print, and regular lists don't. There's a lot of those kinds of like, there's like little bits of polish that make things nicer. So you see that both of these have like the same elements in them, the regular Python list and the NumPy array. But now if I try to do like just this exact thing I did over here, nums, and this might still be pretty fast, but oh, okay. So that takes like a few seconds, you see. Whereas if I do this straight up on the NumPy array, basically instant. And that's because of a lot of optimizations NumPy does under the hood. Python itself is not a very fast language. Of course, everything comes with trade-offs, right? Python's like so relatively easy to understand that you figure you can't just get all that for free. It's mostly pretty good, but it's a lot slower than a lot of other languages out there. And so one of your workarounds for that inherent slowness is NumPy, where they've given you like a Python-like interface to things, but it's actually written in, I think, C++, which is a really fast language. So you get the best of both worlds. Okay, I've been talking at you for like 10 minutes straight. So any questions before I continue? Okay, seems like we're all good. Awesome. So one of the main, let's look at what else I have imported. Okay. PLT, optimization, linear algebra. Nice, a lot to work with. Okay, so a lot of what you're going to be doing in dealing with these libraries is looking up functions and things. Because there's so many functions in NumPy, it's not just like the basic array construction, that you're going to be looking them up all the time. There's no way you can keep them all in your head. You'll remember some, of course, but definitely not. You'll definitely be spending a lot of time looking them up. And that's fine, and that's like the way it should be. So one that I already showed you was NumPy's arrange, or arrange, I'm not entirely sure. And that basically does like what a Python list range would do, except smarter. Another useful one that I always confuse with arrange, and I have to look up all the time, is linspace. So what that does is sort of the reverse of arrange, where in arrange, you are starting with here's a start point and a stop point, and here's the step I want to go through. I want 0, 2, 4, 6, 8, 10. And in order to get that, oh, there's something in the chat. Oh, okay. Range 1e6, right. So, right, thank you for that, because I did sort of skip over it. That's the like condensed version of just saying 1 million. Python does this like scientific notation. So this is equivalent to saying like 10 to the 6, except like the caret symbol means something else. So if I just tried like 10 to the 6, it'll either error out or it'll give me something weird. Yeah, it gives me 12 because it's doing it as like a bit operation, I think. So if I actually want to represent like 1 million, I have to use the E. Yeah. And I think this also works with like 5e6 will give me like 5 million. Yeah. Right. So I was talking about arrange versus linspace, just for like an introduction to like the general structure of NumPy functions. So say I wanted to generate these. I could say either 0 to 10 with step 2. Like I'm saying, I'm going to start my range at 0, end it at 10, and I want to increase by 2 every time. My other way that I could do this is 0 to 10 with 6 numbers in there. So you see the 0, 2, 4, 6, 8, 10, the 6 numbers in that list. So I can either specify that I want to increase by 2 every time, or I can specify I want a length of 6 at the end. And arrange and linspace do both of these things. So let's print np.arrange 0, 10, 2. Oh, that should be 12, right? And it should be 12 for the same reason that like it works the same way a Python range does. And linspace achieves the same goal, except with saying I'm going to start at 0, end at 10 inclusive, and I want there to be 6 numbers in there. And more general things that you can do with NumPy arrays is you can ask for like common numerical things. You can ask for their mean, for example. So if I wanted the mean of this thing that I just printed up here, it'll give me 5. And median would also give me 5. Think of some other like calculations you might want to do, and there'll likely be a way to do them. I'll either say it or we can look it up in the documentation.
Standard deviations?
Yeah, standard deviation is np.std, I believe. Yeah, there it is. Okay. Root mean squared. Root mean squared is a little bit involved. So I will tell you, that's an interesting one for us to figure out together. So I will tell you the following are NumPy functions. You can square them like I did like way up here when I was doing square plus 5 of things. You can take their square root and you can take their mean. So let's try and chain those together to get the root mean squared. So first of all, is there anyone who'd like me to define root mean squared?
I mean, I would. I think it's worth going through.
Yeah. Okay. Let's go to Markdown for this, because if I do it in code, we're just done. There's no fun in that. So it's root mean squared is sort of what it sounds like. It's like those 3 operations that you like chain together. So if I've got like a list of numbers, then let's say I've got like, I forget, is it single? Yeah, it is. Okay. I've got like x1, x2, xn, then, and let's say they're in a vector x. That just means like, that means specific things in linear algebra, but for our purposes, I can just say it means it's like a list I'm putting together and then I'm calling arrow x. So it looks like that, because I kind of skipped over that. Then the RMS of that vector, we can say is square root, that's the root part, sum I equals 1 to n xi squared over, wait, let's do a frac in this. I believe that's it, just off my memory. So it's that quantity, and it's essentially like, it's sort of a measure of like how spread out is this data set, like independent of how big it is. Because like standard deviation is a good measure of that, but if I double everything in a list, the standard deviation is going to go up by a factor of 4. If I want to like control for that, sorry, that this doesn't control for that, but this does control for a list size. If there's 5 elements, there's 6 elements in this, and if I had something with 12, the spread would just naturally go up. If I want some measure of how spread out a data set is that also carries information about how many, that doesn't just go up because there's more things in it. Root mean square is something I might want to try. Okay, so let's try and code that in a Python function. So I've got a function RMS of an array, and I'm telling you it's an array that looks like one of these. I'm going to feed this one in after we're done. How would I do it? First of all, how would I do it without using NumPy? And we can do a from math import square root right here as well. Okay, well, one thing I might try is I've got this like summation in here, right? This like sum over xi squares. So maybe I want to try something that'll make that summation. So let's go over, let's put a for loop in there for x in our array. And maybe I want a variable to store this thing. Sum sq is 0. Sum sq plus equals x times x. And now what I've got over here in sum sq is that summation that's in there in the numerator. What after that? I've started on the hard part for you, but okay. Divide by n, yeah. Sum. So n, what in this case? I don't know what n is.
In this case, we would need to take the length of that array.
Mm-hmm. Length of the array. And then what do I return?
Like we're going to use the square root function from math and call the RMS2.
Yep. So there we go. That is RMS basic Python that I can call on this thing. Okay, so we've got something. It returns answer pretty fast. But now, let's say I made this the linspace one. Should be the same thing because it's the same list. There's 6 points in that. Suppose I said there is 60,000 points. Now it like hesitates a little bit, right? It like takes a second. And that just gets worse and worse the more points I give it. It doesn't scale up very well because it's for every one of those 600,000 points, and you can see like in here, there's actually like that many of them, like it's just going up by like a tiny amount, then another tiny amount, and you can actually still use length and check that this is a really big array. It's got 600,000 points. It's like struggling a little bit. And ideally, I want to write something that has a certain runtime for a small input, and it doesn't get, maybe it gets a little worse with big inputs, but I still shouldn't be able to notice it. Like I am greedy as a programmer, and that's what I want. And that's what NumPy can give us. So let's write the NumPy equivalent of this. What do? I am hinting at these things up here.
So let's start off by squaring all the things in our array, our NumPy array.
Okay, so what do I write?
I mean, we have a couple of options. We can just multiply it by itself.
Yeah, I like that.
Yeah.
So let's say R2 is R times R. And I'm sort of glossing over the issue here of those of you who've had some linear algebra might wonder, what if I want this to be like the matrix vector product of these two? If you don't know what that means, don't worry about it. But there are other keywords and things that we use for that. When I do multiplication, it just means element-wise multiplication. It works the same way as like adding, as I showed you up there. For our purposes, this works fine. So what next?
Still need to divide by n.
Mm-hmm. So, except now I have, well, what am I dividing by n?
So array 2 is going to be divided by the length of that array, the length of itself.
Sure. That works. Let's call this R2n. I'm just lazy on names. 2 over len r. What after that?
We call the np.square root on it. No?
Okay, let's return np.square root of this array. Okay, let's see if that worked.
Be careful. You want
I think we should.
R2n, not R.
Oh, R2n, you're right. Yes, thank you. So
I think we haven't add the elements in R2n together.
Yangshi is a minute ahead of me. Yeah, let's see what we've actually written.
And
that's not the RMS basic Python. Like, remember, this is what we were supposed to get. Now we got a whole array, and it's, oh, well, it's only 6 things. Yeah.
Is that because the division, you're dividing just each element by the length of the array? You need to sum.
That is exactly what happened, yes. So if I print out what I did before and after here, it did 0, 4, 16, 30, 36, 64, 100. And it said, what's 4 divided by 6? It's that. What's 16 divided by 6? It's that, and so on like that. What do I need to do instead?
I suppose you could just sum those elements, right?
Yeah.
Wouldn't it work? Isn't it all linear?
Yep, and I can do
Yeah.
np.sum for that.
Okay.
Wait, I saw a print in there. Yeah, and that works fine. Great, we've done it. And now let's see. Well, let me also point out another thing, which is instead of doing this division by n and then summing them up, you've got to figure, hey, it's a pretty common use case to like average over a list of things, right? Even if I hadn't shown it to you above, you should generally be thinking, hey, this is a really common thing. Someone's probably written a more efficient version of it for me. And that will serve you in really good stead. Generally, if there's like something that's like tedious, but like mathematical, that's not based on your science problem, there's probably a NumPy function or something like that to do it for you. So in this case, I'm going to replace this with R2a for average, np.mean R2, and I get return the square root of that. So really nicely here, I've got like root, mean, root, mean, square. And so that runs and gives you the same thing. And let's see if it gives you the speed up. Yeah, basically instant. So we now know how to write really fast, simple math. And of course, there is more complicated math possible. I'm going to just go. At this point, I think it's about time I showed you the actual documentation, because I've just been like pulling, I've just been like giving you, these are the functions, and how did I learn them? Magic. That's not really a way for this to work. So setup, quick start tutorials, how to, what would be fun? Let's look at tutorials and see. I'll do this, and I'll also look back out. Oh, well, to be completed, really helpful. Okay. Oh, indexing is an interesting one that I should probably talk about. So when you wanted, in plain NumPy, when you wanted to talk about lists of lists, that was the thing you could do. It's perfectly okay to do like 1, 2, 3, 4 like this. And then I can ask for like LOL for a list of lists. I can ask for, in the 0th list over here, what's the index 1 element? And then that'll tell me it's 2. But that's a little like awkward to deal with, especially when you're trying to like chain math operations. Like if it was a pain to do this, imagine how much of a pain it's going to be to like double everything in this array. It's not even like a fun question for me to ask you. So I'll just do it for you. 2 times x for x in y for y in LOL. And that'll do it, but it's like ugly and it's just more and more and more work. So ideally, NumPy arrays would be able to handle this list of list case as well. And very luckily, they can. And so if you've had any kind of exposure to linear algebra, you might notice, hey, this is starting to look like a matrix. And there is a whole suite of matrix operations out there that you can do. I'm not going to go too far into detail at risk of like just making this all about linear algebra and losing all the people who haven't had it yet. But here is the matrix squared, which is distinct from element-wise multiplication by itself. So that's what, when I'm doing like a squared as a matrix. And this is when I'm doing a squared or a times a element-wise. And there's a whole suite of like, you can find like eigenvalues and eigenvectors and do all kinds of operations. And a whole lot of what you'll be doing in physics is actually, like a surprising amount, is just reduce physics problem down to linear algebra and solve the linear algebra. So this is going to be really useful, and the benefits of scale also help us here. The bit that I want to talk about right now, though, is let's make a more fun array to like work with. Let's say I've got a range 120, and I want to reshape that to be 15 by 8. So that's this matrix right here, or this 2D array, I should say. This is a new thing that I've just introduced, dot reshape, and it kind of does what it says on the tin. Also, it might be helpful at this point to remind you that if you want help with any of this, you can just ask for it by saying help of this thing. So in this case, reshape is a method of the array. So I'm going to say b.reshape, and it'll give you the doc string of the reshape function. So it'll tell you, hey, this takes in a shape, which is, they didn't specify it here, but it's a tuple of integers, or just like integers passed in one after another. And it, does what it says. It reshapes the array. So earlier, this was just a length 120 array, and I reshaped it to be a 15 by 8 one. Okay, so now I've got this matrix B, and I can ask for things like its rows and columns. So I can, first of all, I can index into it just like I did before with the list of lists. So say I want to like the third row, second column. Let's see if that did what it said it did. Yeah, row 3 in Python convention is this one. Second column in Python convention is that one. 26, it is 26. And also, just to make your life a little easier, you can just separate them by commas and get the same result. But you can also ask for a whole row at once. That's either by saying B3, and that gets you the whole row, or by saying B3 and this colon. And that just means like slice along everything. And that pretty much works like regular list slicing syntax, actually. So say I only wanted like on row 3, I wanted the first 5. I could put in like a 5 over here, and I'd get suddenly from this whole thing, I'd get this part of it that I wanted. And the same thing works kind of in reverse. I can slice along here, and now I've got like up to the 3rd row and up to the 5th column. And so you can get like subarrays this way. And that's a really useful feature. Also, a lot of functions are going to take in an argument called axis. So over here, if I wanted the mean of B, it'll just sum them up the same way it would in a 1D array, because it's implicitly assuming do it over every dimension. But I can also specify, hey, I only want you to do this over the 0th dimension. And what that's going to do is it's going to average over this column, over this column, over this column, etc., and return that separate thing. The array of each individual mean. And similarly, I can do this over 1 and that's going to do it over every row. So this is not yet another case where we see, like, I'm not going to say parallelization because that's got a different meaning in computer science as well and might well be something you come across, but you see the benefit of doing things all at once rather than putting this in like a for loop and saying, oh, for every one of these, I'm going to figure out exactly which indices to look at. I'm going to take a mean over those by like summing them up and dividing by the length. This is way easier and way quicker and will just make your life a lot easier. Okay, we've got 13 minutes left. In that time, I want to show you a bit of the basics of plotting. Now, there's going to be a detailed plotting notebook in semester 2. So I won't go too far in depth over here, but we can make a data set and look at some of the ways to look at it, because having quick looks at your data is a really useful skill and might well be useful when you're debugging the module later on. So the module has you make a physics simulation of a double pendulum. And if you've taken physics 7a or something like that, you might have seen the single pendulum, you know, the thing of like, you've got a support, you've got string, and it just goes back and forth like that. And it's like the simplest form of an oscillator. But if you add another weight to the bottom of that first weight, and here I really wish I had like, why am I not like a 1900s hypnotist that just has one of these? But yeah, if you put another weight on the bottom of that first weight, it'll turn out to exhibit chaos, which has, again, a rigorous definition that I don't know all that well. But essentially, it's going to do like really weird and unsurprising things just from like such a simple system. And like some of the justification for that is the algebra is really ugly, which suits us because the algebra being ugly is exactly the kind of case in which you would want to do this kind of simulation. So you're going to see some really interesting results when you finish the module. And so I'm excited for all of you to do that. But it's very likely that while you're working on that, you're going to see something going wrong. Give me a second here. It's likely you're going to encounter a bug and you're like failing one of our test cases. And so as a first line of defense, you might want to try plotting your output. You know, you've got like a pendulum doing unexpected things over time. Let's see what it's doing over time. Maybe it's just like going to 1 and staying there. Maybe it's got the negative of the value that I want. It's not very intuitive to like probe that by like printing lots of values. Printing lots of values is a great skill, but sometimes you just want to like look at it and you want that to like tell you a story. And so the basics of plotting syntax, while not exactly in scope for this lab, for this module, I mean, are going to be pretty useful, I think. So the basic function that you want to use is plt.plot. And so that's in the matplotlib pyplot module, which I imported way at the top with this when I was optimistic about getting to like optimization and linear algebra. How naive I was 40 minutes ago. Yeah, so that's the import line that you want to use. This basically means it's like a Python implementation of a MATLAB plotting library, and MATLAB does plotting very well. I'm not generally a fan of MATLAB, but it's got its niches, and plotting is definitely one of them. And so a lot of the NumPy plotting syntax is just copied directly from MATLAB. But we don't need to deal with like all the complexity of it. We can just use it as sort of a black box. So in its most basic form, it can just take in like a single array. It can also take in a list, but usually you're going to be passing in arrays because of all the reasons arrays are better that I hope I've proven to you by now. So let's say I wanted to make a plot of the mean of B. And there we go. That's a not very informative straight line. Now, I've committed some cardinal sins of graphing here. What do you think they are?
Well, we're missing some labels, some units.
Well, in this case, there really aren't any units, but you're right that you're missing, but you still would want to say it's unitless. So it doesn't particularly matter if you're just probing it like for your own use, but in general, you do want to put these things on there. Like, I have no idea what this is plot of. And seeing some things in the chat also. The axes are not equal axis labels. Yeah. Okay. So let's put, the thing is this this data set doesn't particularly mean anything. Okay, Taya's asking, what does axis equal 1 mean? Okay, great question. Let me cover that and then I'll go back to the thing about plotting. So in a NumPy array, there's multiple dimensions. In this one B that we were dealing with before, there is the dimension of I could go along the rows, like I could go along this row, this row, this row, or I could go like top to bottom, this whole column, this column, and so on like that. So the axis is a keyword indicating which one of those do I care about at the moment. So axis 1 over here means I want to have a result for every column. Wait, it means, sorry, let me get this exactly right. It means I'm summing over the rows. And I will therefore get a result for every column because 0 is not in there. So this sort of goes outermost to innermost, because this still has the structure of like a list of lists, right? Over here, I've got a list. Within that, I've got the list representing the first row, the list representing the second row, or the 0th and the first, and then list representing the index 2 row, and so on like that. So axis equals 0 means I want to look at the whole thing. And axis equals 1 means I want to look like one level in to the particular row. So what I'm doing over here is I am summing over every row, which is the like innermost one. And this syntax extends as well. I could make this a 3D array. If I could say like E is np.reshape, np.arrange 120.reshape. Give me a good factorization of 120 into 3 numbers. 358, let's do that. Oh, well, I guess I screwed over my example here. So now here I've got a list of lists of lists. And the syntax isn't any worse to deal with because I've got this like axis way of looking at it. So this is really useful if, for example, I've got like, this is a real life use case that I use. If I'm using with like image data and I've got like, here's my image at time 0, here's my image at time 1, here's my image at time 2. All of these images are going to be like 2D arrays of this is what's on this pixel, this is what's on that pixel over time. So that has to be a 3D array or a like stack of 2D arrays. So these do come up quite a bit. And if I want to do the mean over axis 0 or B axis 0, what that's going to get me is it's over the top level one, over the one that just looks at, it's trying to average the list of lists. Because it's doing 0 plus 40 plus 80 divided by 3 is 40, and so on up like that. If I want to do axis equals 1, it's going to go down to the next one. And if I want to do axis equals 2, down to the bottommost one. And I can also specify multiple ones of these, I think, at a tuple. So if I want to sum over axis 0 and 2, but leave 1 intact, it's going to be that. So it's just a way of specifying what like level of depth of the array am I at. Okay, we've only got a few minutes. Let's get back to here. Whoops, I have accidentally shown off a feature I didn't mean to show off. So over here, any ideas what's happening since I redefined what B is? Why am I getting tons of lines now?
I mean, you're basically plotting each one of those like levels that you had.
Yeah, that's perfect. Thank you. So basically, like now this quantity over here has multiple sets of data to it. So it's plotting each one of those. That is more lines than I expected, though. Let's just, yeah, this is a little nicer visually. So basically what I did there is transpose. I like flipped which ones are the rows and which ones are the columns, just for the sake of like, I wanted to be nicer to look at. So actually over here, this lets me show off the legend a bit more. So now I've got 3 lines and I don't know what any of them mean. I can give it an x-axis label. This is sort of a meaningless data set, so there's no real like meaningful label I can give this thing. Row of the submatrix index. So like this is, each of these is like over a, yeah, they're over like a sub-row of B. So I might as well say this. It doesn't really matter just for the purposes of demonstration what I put over here. It's just to say I can put labels on these things. And in here, if I wanted, I could put like unitless, or could I specify that? And if I have multiple plots as well, let's say for row in, and this is fine to do a for loop over because it's just 3 of them. I can give each one a label. And let me actually put an enumerator of this just to drive the point home. So matrix format I. Wait, something changed. Wait, I think I don't need the transpose anymore now that I'm forward. I think that was it. Yes. Okay. So I've like given this whole thing an x-axis label, a y-axis label, and for good measure, I can title it. And that'll give it like a title on the top. And Matplotlib is actually really clever about this. It'll reposition where it puts this plot for just based on how crowded or not crowded, or sorry, where it'll put its title and its labels based on how crowded or not crowded everything is. So this is sort of the default position because there's not a lot going on. And over here, I put a label in, but it's not showing up. So to make it show up, I do plt.legend. And so over here, it's going to tell me submatrix 0 looks like that, submatrix 1 looks like that, submatrix 2 looks like that. So those are just the very basics of the plotting tools you will not necessarily need, but will be very helpful as you debug your CS module 4. All right. Any questions as we wrap up? Okay, seems like there aren't any. All right, good luck doing CS Module 4. A reminder, I'm doing office hours Thursday, 6 to 7. I'm really excited for everyone to do this assignment, so good luck. Right, bye everyone.
Thanks for the lecture.
I'm not sure if there's a checkoff. By note, and also Neil, by notes, do you mean this notebook? I can just upload it to Slack once we're done. Okay, yeah, I'll upload it to Slack. I would imagine there's a checkoff, but I'm just going to check with Yi about that. Let me just text him. On screen share, and I will upload this thing.